talk about it. So please contact us and we will help you kind of navigate that. Besides this class, you know that you're going to need to have this skill anyway in any career you choose. Okay. Framer. So this week, so a couple things about section. Hopefully everyone's kind of at least launched off a little bit on program assignment 2. This is a more complicated programming assignment. We didn't really talk about it much last week because I wanted to spend time on the brainstorming activity, but this is a more complex assignment. There's a lot more issues of dealing with APIs, talking to the watch, lots of things like that. So the GSIs and the teaching staff are sort of shifting away from dealing with all the setup issues. We need to focus on more instruction around working with some of the APIs and the bigger parts of the assignment. So just that's mentally what's going on. So we're going to also be introducing you to a tool called Framer. Who here has used Framer before? Okay, it's fine. We're going to show you all of the great things about it, so don't worry about it. It's another awesome bonus. Framer, retail price, $99. Actual retail price for CS160 students, free. See, you already won something. The game show is moving along nicely. So we have licenses provided by Framer themselves to everyone in CS160. And Cesar, I believe, or one of the GSIs posted that information last night on Piazza or B courses. What that means is don't come to section and go, hey, what's Framer? Oh, I got to get online and download Framer. There's instructions on you go and you buy it, but then you don't pay and you enter this code and then you get it for free. You will hopefully love Framer because it's a really nice intermediary programming tool that's very lightweight programming that lets you actually work more as a designer on designing interactions and visual kind of experiences rather than struggling with all these issues of callbacks and things with Android Studio. So it'll be a welcome, probably relief to get things really interactive right away. It's actually fun to play with. So bring laptops, that's the information. Watches, we're going to be handing out the watches very soon. Look for a message about that tomorrow. And that I just don't want to say much about that, but they're coming very soon. And there'll be details on how to do that. And possibly the person that is the designated leader of your group will help coordinate that. You also saw we put this message out on I believe, Piazza last night. So what we've done is everyone has like a group number. You're welcome to form a group name. You don't have to be group 12. But for simplicity, we have to kind of work with numbers because I can't keep in my head every group name. And one thing is we're going to be moving more into the studio model after the midterm. And we want it so that you have an immediate GSI contact for your group. So if whatever your group number is, these are the sort of contact GSIs. It's not that you can't contact anyone, but that person, at least myself as the professor, when I want to know what's going on with, say, your group 9, I will go and say, okay, Cesar, what's going on with group 9? And so he'll hopefully have at least the best knowledge, maybe not complete knowledge, but you can imagine with 200 students, we're sort of having to deal with, we really want to know you and your projects and the groups, and so this is a way for us to kind of do a little hierarchy. Questions about that? All right. So before we get started, I want to go backwards a little bit because two things. I wanted to show some projects that we had done before and look at them. And just a little critique so you can see how people in the class did on other assignments. So for example, programming assignment 1 and design assignment 1, which I will do after lunch actually. And then also after lunch, I want to critique some things that, I don't know if you remember, it was a couple of weeks ago, I said if you want to talk about different designs or interfaces, put them on Piazza. So I pulled a couple of those for us to talk about after lunch. But I'm going to talk about programming assignment 1. Is Henry here? See, this is where you figure out if you come to class or not. We might call you out. Okay. So this, I'm going to show, I think, 3 or 4 examples of programming assignment 1, mainly because they all have different kind of nice elements. I just want to talk about them very briefly, and also so you can get a sense of the full design range that people chose from, the trade-offs of what worked and what didn't work.
it allows us to convert images between different types of animals, including humans. So for example, let's to select the first animal that you want to convert from, you select which animal at the top. And here you can scroll through it, and let's say we want to convert from rabbits to Aussie ears. So selecting Aussie at the bottom means that when we enter something like 50 rabbit ears, we know that it's now 11.25 Aussie ears. Now let's say we wanted to select something else. What is 50 groundhog ears in something like wolf ears? Well, we now know that 50 groundhog ears is 38 wolf ears. It's just that simple. You select an animal at the top, enter the number of years that that animal age is, and select the animal at the bottom, and that's it. You get the number pretty easy on the right side.
Okay, what do people think of Henry's piece? Good? What are things you like about it, basically? We can give it a little bit of a critique. The visuals, in terms of iconography. It is nice iconography. A lot of people did find some clip art like that. That's nice, yeah. Yeah, no, that's fair. There's not enough contrast on the text with the blue on the bottom. Right, so you select the animal. It does appear in this sort of light. It says like groundhog ears, but it doesn't sort of keep that highlighted. I think that's true. I kind of have to watch the video again, but yeah. What do people think of this sliding interface? Yeah, that's a nice way. If you think about it, the one challenge that maybe you weren't clear that we gave you was we gave you a lot of animals that you had to somehow figure out how to deal with screen real estate, and everyone kind of dealt with it different ways. Henry basically did the sliding interface. I would say when you do those, you need to make sure that it's clear that is a sliding interface, because you might, if you didn't see that hint at the side, you would think, oh, I can only choose from these three and maybe the three at the bottom. So they're important to have these visual cues to let people know that there is either a way to gesture or a way to get to more animals. Yep. Anything else? Yeah. Yeah, it's pretty reasonable color choice in the sense that they're at least clearly differentiable, and yeah, they're matched. There could be other ways, and we'll talk about graphic design, I think, next week, visually how to tie things together. Some of it actually we talk about today. Okay, let's look at another one. Sean? Here? Not here? See? Okay.
UAnimal is an animal age converter. All right, let's get started. So we're at the home screen of UAnimal right now, and we can get started by tapping the UAnimal app icon right here. So now we see the main screen of the app. On top, we see a card that tells us what the app is and how to use it. So it says to enter age for one of the animals, and then you get the equivalent age display for all the other animals. Let's try an example. So I am 21. And I want to see how old I am in cat years. So I would tap human because I'm a human. And then I would enter 21. And I would see that if I were a cat, I would be 6.6 years old. As another example, let's say I have a dog that is 7. So I tap dog and enter 7. And I would see that my dog would be 25.5 years old if she were a human. All right, now as a final example, let's try this out. So I know that humans live for about 71 years. So if I enter 71 right here, and I look at all the other animals, I can get the approximate lifespan of all the other animals. And here we are. The top card can be dismissed, and also the keyword can be retracted if you want to see more animals.
Okay, thoughts about Sean's? Yeah.
I like how we were able to see like all of the animal behaviors, like with mapping like real estate, but the only problem is like the pictures, they aren't like tinted with any color or blurred in any way, so it makes the text a little bit hard to
Yeah, thoughts about, yeah. So it's nice. He used kind of a card system. So these are all these cards, and you basically made them so that any one of them is selectable, and they all affect the other ones. But right, so like that hamster has some white background, and if you had white text on it. So again, you need to have enough contrast or something that visually would pull that out. Luckily, I think he at least chose a very large sort of sized lettering for this. So the font choice is large enough to at least pull that out, but that's true. So this is another approach to how to deal with this long list of animals. Other comments? All right, we'll look at a different one. All right, Donnie. Donnie? Yay, you're here. Yay. It looks better than this. This is some encoding problem. Hold on.
Hello there. Welcome to Animal Age. Animal Age is a fast, simplistic, surprise Animal Age converter. When we first launched the app, the default screen shows a dashboard of all the required animals. At the top, you can type the age or choose the animal to convert from. The sentence reads naturally, like how you would speak. For example, if I type 21, it would say 21 human years. Or if I type 1, it would say 1 human year. And the polarization rule also applies to all the cards in the dashboard. In addition, you can also customize the dashboard to include only your favorite animals. Just go to the action button, go to add and remove animals, and you'll see a list of animals that can be chosen from. For example, if I don't like deer, I want to keep only cat, duck, and wolf. I can just toggle these animals on, and when I go back, you want to have these animals in my dashboard. And as usual, if I just type in my age, pick an animal to convert from, and answers will be reflected on the cards instantly. Of course, the preferences I chose will be saved even after the app restarts. So if I go to my animals list, take a few more animals. As you can see, they're in my grid view. You can quit that app and restart it again. They will be here waiting for you.
Okay. Oh, I forgot he does show one more thing.
Orientation, which I cannot show through the video here, but you can check it out on the project website to see the landscape screenshots. Thank you for watching. Bye.
Bye. Okay, what do we think? Another strategy, yeah. Right, so the question is there a select all? I don't know, we can ask. Is there a select all? I don't remember. No. Okay, good. It's good when you're in the room. Yeah, so you might, obviously, that's something that would be nice, because what if you want to bring them all in? I just want to show, first of all, another strategy for dealing with lots of lists. Right now you can have some kind of optional screen to select the ones you want. It saves some state so that as you quit and exit, it sort of remembers them. There might be ways you want to order them or something like that. Pretty nice. There's some iconography, and also the lettering and the numbers are not overlaid across something that with some other busy background. Other feedback? Okay, I've got one more. I know you've forgotten about this assignment, but it's pretty cool. Alex.
Right here.
Yes.
Okay, so here's my UAnimal app. So we use a horizontal scroll view on the top and bottom to select your source and target animal. So let's say we want to convert sheep ears to human ears, and we enter an age by 4.20, and we'll see that 4.20 sheep ears is 0.788 human years. Now, even after you type in the age, you can go through and select different animals, and it'll do the new conversion as you have your new selections. And then another thing to note is that if we exit the app and re-enter the app, the animals that we last selected are actually retained because we saved them into our preferences. And now, let's say we enter another age here, select some kind of animal. We can even share what results we get to our favorite friends. So let's text this to Apollo. And there we have it.
Okay, so to further confuse you in the evening when you get that late night text, 5 pig years are 37 animal years. Like, okay. So great. Feedback. So I think, first of all, we saw the sliding is another, we saw this strategy come up again. Some good sort of visuals and color choices, things that are drawing the kind of visual language together. Other feedback or comments? Yeah. Right. Yeah. So we'll talk about contrast a little bit during graphic design, but another good point. Oh, yeah. Yeah, I thought about those choices. I mean, there was the assignment, which was do what we said. But if you thought as a HCI researcher, how would someone really use this long term? You might configure it for, say, you and pets you like, for example. And maybe you always want to just kind of think about that. So you maybe don't care about hippopotamus, right? So you might say cat, dog, hamster, things like that. So you might want to save those preferences. That would be really cool. Yeah. Yeah, so the way that it sort of hints at that. Okay, good, great sort of feedback. So I do have ones for design, but I'm going to save those for probably a little bit later because I want to get into some of the topic for today, which is a really sort of very different approach. So we've done some things so far with HCI in terms of we've gone out and sort of done these informal interviews. We've done prototypes, showed it to people. We've talked about contextual inquiry, going to people's place of work or their context of work and doing these observations. We've talked about maybe these more discount methods, sort of heuristic evaluations, going through and looking at violations. The other way is, in some sense, the more sort of scientific way. What if we actually just try to model a human? Like, you know, we do not have superpowers, so we have limitations in terms of the kinds of senses we have, the kinds of memories that we have, and sort of the way that we can affect our world through, you know, gestures and motion and those things. So this is a concept of how we can think about just modeling that, and we can draw from empirical studies that have done observations of humans, and we can then say, if you design this interface, we can say things about it that this would be difficult for a human, okay? Because, well, maybe some other space alien would perform well because they have better memory or better dexterity, but for the constraints of a human, we just apply this, and we don't have to pay subjects. We can actually just know from the model, this will be a bad interface or a good interface. And here is the spooky picture that's often used for this. Okay. And this is thinking about, I mean, many of you are computer scientists, so this will sort of feel natural, but okay, let's just think of the human as a processor. There's a perceptual, so how you take in information, in our case, mainly visual, but you could imagine this would apply to things that are tactile or auditory, things like that. There's a cognitive processor. How do you process things? That requires some amount of non-zero time to think about things. There's also motor. So how do you actually then send a signal out? How long will it take for you to respond? And there's also things with memory. So people build up memory in terms of short-term memory and long-term memory. And then there's this unified model that's been put together. And the reality is it's probably inaccurate, right? And there's no way you can just completely model everything about a human. But this approach works, and you'll see how we can take small parts of this approach and they work extremely well. And as it says, you can really predict performance. Okay, so here's this model, and I'm going to walk through all the different parts of this. So you saw this in the reading, and I'm going to basically just try to walk through what some of this was in the reading, so I'll go through it quickly because you're probably familiar with it. But for each of these, there's different properties. So in terms of the perceptual processor, there's some things you want to notice. So there's a sort of time that's required to perceive something, and I'll show a little bit more examples of that, but it is not zero. It takes some time for you to actually perceive something. Is it like a letter or a color or things like that? And there's also a sort of capacity to these, and there's a decay for memory and such. So let's look at them. So for the perceptual processor, at least what we're talking about, where most of the time you're looking at a screen, this is the easiest example. Obviously, it could apply to other senses, but you're sort of perceiving some sound, some light, some touch, and you're sensing that, and you can select things that are what they call pre-attentive. These are things that require less processing time for you to actually perceive. And the capacity of the visual store, through lots of empirical studies, is sort of 17 chunks or letters. So it's kind of how much you can perceive. And the decay time for your working memory, so when you kind of see something, around 200 milliseconds until it's sort of you sort of the memory's not there. Now, there's ways to actually keep that around. And you can transfer things to working memory as well, and that just takes some time. So what's this pre-attentive thing? These are very important cues for you as an HCI designer, because if you know them and you know how to use them, and you don't overuse them, that's the other problem. They're typically tasks that can be performed on large multi-element display in less than 200 to 250 milliseconds. They're considered pre-attentive. So here is an example. How many 3s are in here? Oh, is it not working? All right. Pretty hard. Let me give you a different one. How many 3s are in this one? Easy. How about this one? Easier. These are because we're using perceptual cues that actually allow that selection process to be pre-attentive. Okay? It means that we have played into this bias around color that humans are very well attuned to noticing. Actually, let me see if I can. So they are different kinds of qualities. So here's one of them that you just saw. So we're very good at color. So if I tell you, how many red circles are on each one, you can sort of easily pick this out. It takes very little processing time, very little cognitive load. These are the kind of things that interfaces play into to help you out. It also works with shape. So how many red circles are in this? Okay. We're good at shape, and we're good at color. How about shape and color? The conjunction. How many red circles are in there? Harder. Unless you have some superpowers, in which case you should report to the special superpowered legion. Yeah, it's harder to have both of them conjoined. So it's not as if more is sort of better. Let me flip to something here. If I can do this. I'll try a little game. Okay. This little square here, let's see if this works. Right. So what this does, let's do this for a second, is you're supposed to look for how many, if not even how many, just is there a red circle, okay? So if we do it by color only, easy. Let's do one. Well, maybe, I don't know. Depends if if people with visual or sort of, if you're unable to detect color correctly, then that is a problem. So you're looking for the red circle. Now, when they're conjoined, right, so much harder. That's 400 milliseconds. That's all you're seeing that image for. Okay, so so these pre-attentive features are really important to basically understand, and they allow you to make designs that actually, oh shoot, there's an image missing there. That's a key image. Hold on a second. I just realized something's missing here. Oh, but I have the image someplace else. I have the image. I have the image on this web page. The image is on the slides up there. Oh, yeah, we have it here. Yeah, this is important to talk about. So there's certain things that are sort of pre-attentive that humans can get a better sense of, and some that are not. So you already saw some that were and some that are not. So things like lines, we can tell orientation. You can very easily, in a pre-attentive way, you can tell that that one line is not parallel with the other lines, okay? Length, we can very quickly, pre-attentively see the element with the longer length. Closure, you can see very quickly the ones that have are closed kind of connection. I think there's just one in there. Similarly, size, curvature, we can detect things that are different in terms of curvature. Oh, great, thank you. Yeah, that's fine, yeah. These density, you can sort of detect that quite easily. All of these are important to notice because these are elements that you can embed into your visual design of a user interface. And there's lots of different ones. Okay. You can tell one of those lighting directions is different. The direction of motion, all of these things are visual designs that you probably, even some of these you can tell are things that are used in actual interfaces. Okay, back to this. Let's talk a little bit more about that perceptual processor. The key thing is these pre-attentive designs are really important. We know that from these empirical studies. Now let's talk slightly more about the cycle time. So when you see the world, you see it at about 100 sort of millisecond chunks. If you think about it, that is exactly kind of how movies work, right? Movies are not continuous. It's one image and then so many milliseconds later, another image, and your mind stitches it together. But we need to play into that in terms of the way we design interfaces. So the frame rate necessary to achieve movies, about 10 frames a second. These are sort of same things around the maximum Morse code for people to perceive things. But also, you'll see how it plays into the design of how you relate causality on an interface. So what happened? Red ball hit blue ball. It's usually what people say. The point is that they occurred so close together in time that the causality was built in your mind that one caused the other. Okay, little longer delay, very different effect, okay? This is important because if you have something in your design that something happens, you want the user to know that that action related to some effect. These delays can cause a visual and like mental kind of break from that. And the studies, this is sort of some of them that kind of summarize this, that people, when you ask them about if there's an immediate causality from some event, if the time before the second object moves starts to go too far away, they classify them as totally independent events. Now, it's also good if you say, I don't want these related, then you need to make sure there's a delay that separates that so that people understand that. All right, here's a little bit more of this. You saw this example, right? This is the one I just showed you, but I wanted to show you a different variant. What was that? That's like red ball chasing blue ball. That's what most people say, okay? That's blue ball following red ball. Okay, this is the way people in studies describe this. It has to do with the size and that the red ball feels threatening to the blue ball and so it's chasing, but in this scenario there's following. These are other things about size, color, and the motion. One was a little bit faster. People thought that was a sort of chasing. These are all things that as a designer you might think, I don't know, just make them move across the screen, but people will interpret it in very significant ways that you might not be aware of. But now you're taking CS160 and you know that. Okay, so let's move on to the working memory and talk about it for a little bit. So I mentioned this idea of kind of how you access things in chunks, and the magic number is this 7 plus or minus 2. There's actually a famous paper, it's called something like the magic number 7 plus or minus 2. So this studied these chunks that people can remember, and it does depend on age and other issues about cognition, but in general, people can remember. If you look at this graph here, it shows the percentage that people recalled over time. Now that's showing you the decay. So if you ask someone to remember one thing, a letter, something, they do a fair job at sort of remembering it over roughly, say, 73 seconds. If you give them 3 things, usually about 7 seconds, and so on. So the other thing to note is that interruptions actually can disrupt this. It's important, again, from a design standpoint, because if you tell someone, you put something on the screen that they need to remember, and then you disrupt them with some other task or screen, and you ask them to remember that, it just won't work. This seems intuitive, but this might be done in very subtle ways where it's just them remembering a direction or a color or something. You've probably encountered this when you go through different screens and you can't remember something. Someone has violated this 7 plus or minus 2 rule. So you can commit things to long-term memory. So all of us have long-term memory. Remember that cool tree we used to climb as a kid? Somehow that's stuck in there. So great things, very large capacity. It's kind of like endless. We don't ever sort of go, well, I better delete things from 3rd grade. I need to make room for sort of class homework assignment today. It's not really how it works. It's a fast read. You can use to recall things. There's some caveats to that, but it's expensive to write. Usually you spend some time in studies they've looked, and people spend time thinking about something like, oh, I definitely want to remember like the first time I came in Jacob's Hall, and you're sort of thinking about it, then now you remember that. And you could move things from this sort of working memory to long-term memory by rehearsal. So if you rehearse something, it usually commits it to memory. That's another strategy. Now, one thing about retrieval, often you need other context to retrieve things. So you might easily be able to remember your first kiss or something from your childhood, But other things, you need to remember the context. So it's not just trying to remember the actual fact. You know, who was my first, I don't know, person I met at Cal or roommate or something. You have to kind of remember, oh, I was in that one dorm room or that one place and it was dinner time. There's other context. So there's usually some time and there's other context you need to remember. What that means from an HCI design standpoint is that if you know during your design that you're going to have to get someone to remember something from long-term memory, you want to give them cues to get there. So you want to give them other information that will help them understand how to get and how to retrieve that information. Okay, so our picture again. So let's talk about the cognitive processor. So this is basically sort of actually the brain, the computer, what's happening. So once things are brought in, you perceive them, maybe they're preemptive, maybe you've brought these chunks in, you've moved them in to memory, now you're sort of going to do some operation on it. Usually we think of the cycle time of a basic operation around 70 milliseconds. Obviously, as I mentioned at the very beginning of the lecture, this is not some exact thing. You're not clocking your brain at 70 milliseconds, but these are empirical studies that you can model lots of behavior this way. So if you want to match some digits, it's usually 33 milliseconds. You can see that, you know, if you just want to detect sort of colors and to determine that, there's different studies. But it's one thing to note is when you're doing this cognitive processing, it is usually a serial operation. So I know many of you are like, no, I'm totally like a superstar. I got multiprocessors, man. Check me out. But I'm sorry, the studies do show that you do kind of one thing at a time in an internal fashion, and it creates a problem. So these little notes below relate to when you become so focused on that cognitive task. So this is like an airline that was basically, the pilots were so focused on one element of the design, which was some landing gear light indicator bulb, they became so focused on it that they didn't see these other things happening, even though there was alarms and sounds and the plane crashed. So it's not as if good designs really make this work and it's a more pleasurable experience. I mean, as I mentioned, even the first class, HCI, it is also about life and death sometimes. Okay, finally, let's talk a little bit about the motor processor. And so that's now, for example, how you actually say move your hand to control the mouse or something along those tasks. And you receive input, the cognitive processor has decided hit spacebar. Okay, that's the command. And then you have to execute that. And there's lots of studies about how fast you can move your fingers. It depends on the task and how expert you are. There's also sort of what they call a point of no return, where your muscles got the signal. You're not going to stop it. It's just in whatever, so many milliseconds the act is going to happen. The sort of scribbly scratches, if you remember from the reading, are really about how the task comes in. So if you tell someone to be drawing quickly between those two lines, but they're asked to kind of self-correct, that means the cognitive processor is coming in and it's going through that whole visual loop to correct it, and it's slowed down versus if it's open loop. So there's different measurements of how the motor task actually works. So I'll just walk through a very basic example of this. So the task is the awesome hit spacebar when character appears. Okay, boring, but it illustrates how even if you design something where you say, okay, something's going to come on the screen and they're going to respond, you might ask the question, how long should I expect until they can actually respond to that? So something comes on the screen, it has to be kind of perceived, so it has to go into working memory. So that takes sort of a cycle of the perceptual to get in there. That's this tau p for time, sort of in the perceptual. And then it has to move into the cognitive processor, right? And then the cognitive processor has to cycle and tell us that is a letter, hit the key. That's this tau c for the cognitive processor, and then finally out to the motor again. And there's the motor's finally told, okay, you can sort of hit the key. And I gave you those numbers before. You can sort of add that up and figure out how long it might take someone to actually respond to that request. It gets more interesting when you put in something more complex. Like I want them to see these 5 letters or colors, and if there's a blue one, then they should answer a certain question or whatever the response is on your interface. But it gives you a chance to say how long or how challenging something will be, and also because you know these limitations, you can easily say, wait a second, they are going to not be able to remember that whatever letter, because by the time the processor cycles back around, it'll be over so many milliseconds, and we're over 7 chunks plus or minus 2, and so there's no way for someone to really, they're going to struggle with this task. So as cool as this method is, it also is not perfect. I don't want people to sort of walk away and go, oh, we just solved HCI, we're just going to use this model. It's only sort of dealing with this very low level loop of humans, but think about the things you do in life that are much broader, social things, things that are at a much larger task of strategizing, life goals and other things. These are harder, much harder to model. So if you think about it, the interface should respect limits of human performance. These preemptive features are great. They should be used when you can. Events with cycle time will fuse together. That's either good or bad, depending on if you want things to feel as if there has a causality or if there should actually be independent. And then recognize and act cycle that I just sort of walked through. You want to basically think about the load that that's putting on people. All right, let me say a little bit more about memory. So let me do this. Who wants to volunteer for this? This is a cool, fun volunteer thing. All right, got to come up because we have the cool microphone. Ladies and gentlemen, here comes our volunteer. What's your name? Tim is coming up. Tim is here as a student. Let's welcome him. Okay, so here's what he's going to do. I also need another volunteer to do timer mechanism. Who can take time? Who has something that can take time for us? Okay, here's what we're going to do. He's going to start saying colors that you see on this list of words. When the slide comes up as fast as he can. And he will say done when he's finished, and you have to tell us what the time is.
So this is the colors that are...
The colors that you see of words.
Okay. Red, green, brown, yellow, blue, white.
Fun experiment to play. Okay, so let's obviously you know where this goes. So you're talking about the actual color, not the color word. I know this game, but it's still fun to play. All right, Tim, go.
Green, white, yellow, red, brown, blue. Done.
All right, what was that time? Okay, did pretty well. All right, awesome. Thank you, Tim. All right. So I know you've seen this game before, but it's one of those fun ones that also illustrates how conflicting signals coming in, and Tim struggling to try to detangle them because the words. Now, it'd be easier if I'd put up another language that he obviously, if Tim didn't speak that. These are these interference, the stoop effect, when a color spelled out by word is incongruent with the color used to show the word. And you can actually get tied up in this with user interfaces too. The relationship between the meaning and the physical form of the stimulus are basically in conflict. So the thing to think about is in terms of how you stage things for people to sort of visualize and sort of process. So remember, all these things are going on at every moment during someone working with any design that you've made. They're sensing some image that's actually slowly decaying. They are not going to remember it forever. You have a limited amount of time that they can move something into working memory. That will also decay if you don't do something about it. What do you do about it? they can actually do some kind of maintenance. You can remind them. This can be a rehearsal or a strategy to move it into long-term memory. Eventually, there will be some decay or interference that's hard to predict. And then pulling things from long-term memory also has this problem with chunking. And this sort of stage theory stems from the fact that really working memory is small. It's temporary, it decays, things displace it all the time, especially if there's interruptions. We talked about that. So you need to have some way of rehearsing and remembering these things, especially if they're important for the interface. So a little more about long-term memory. It recodes information, and it's often organized. This is into your long-term memory. And you need it to relate new material to already learned material. So in fact, things we talked about earlier in this class, the skeuomorphism that helps us relate new user experiences to old, these are kind of play into this. Links existing knowledge to categories. And often memory needs some kind of attached narrative. So it helps people remember. Think about how maybe many of you remember your password. It has some kind of, this is a long-term memory, and you have to remember some meaning behind it. But maybe your password is just CS160, in which case you just remember that. And what this really gets at is something we talked about before. These topics kind of resurface all the time, this recognition over recall. We talked about this several weeks ago, but this plays exactly into this model and derives from this model of long-term memory, that people do better recognizing something than recalling it. The example I showed many weeks ago was remembering some command line for deleting a file or moving a directory versus just, oh, I just drag that over. That was sort of, or something on a menu screen that's something you would recognize. So we want to design user interfaces that rely more on this recognition. And when we do want people to try to retrieve something, we need to think about strategies to provide cues. So hints, so having different kinds of icons or labels or menu names that are consistent, things that will help us to retrieve that information. And also this idea of situational. So we talked about how you often need to bring in other parts of context to remember something from long-term memory. All right, so the summary for this part of this kind of human model processor is it's roughly 5 parts. We walked through them. There's a perceptual processor. We talked about working memory, long-term memory. We talked about the cognitive processor and how that's the part that actually does the computation. These all take some non-zero amount of time. They all have these decay properties. They all have limitations. They can't hold infinite amounts of information. And then finally, this motor processor to send things out. Caveat, it's like this is not 100% accurate, but these are good at getting first pass estimates. And like I promised, I'll show you some subsets of this human model processor that are extremely accurate for HCI design. So interfaces should both aid and exploit the human capabilities. All right, let's talk about some other perceptual and sort of limitations of human cognitive load and design kind of constraints. Who hates this situation? I hate this. I literally waste some non-trivial amount of my time going, I just don't know. I just want toothpaste. I think, what insane manufacturer is doing, like, taking my life away? I have to actually look at all this stuff now. Like, I don't know. I like whitening. I don't know, but like, it's too much, right? So obviously this mimics this, and people have written about this a lot, but too many choices, not only it can kind of, at this extreme, it kind of paralyzes you. I would literally like stand in the aisle and go like, help, I just can't even deal. I kind of wish I could just say, whatever I had last time, just pop out at me, just visually pop out. This is like, I can't believe I have to like parse through this. So this paralysis, that happens in interfaces, right? So it's not as if you've never been presented with too many choices in an interface. That's all the sort of menu options exposed. Or maybe something like this. What do you want to watch tonight? Oh, man, I don't know. Like you start scrolling and looking and back and forth, and then you watch nothing, right? Okay, it's okay. It's a confessional. We're admitting that. That's what we do, okay? It's like, it's not always Netflix and chill all the time. So No, it's too many choices, right? So this is not as if it's just, yeah, we know that, quit telling us stuff. Again, people do empirical studies of this exact phenomenon. So it's called Hicks' law, and it's the cost of taking a decision. So if you have to choose between n things, actually it's sort of n minus n plus 1, because you can also choose none, but for the sake of keeping it simple, it shows that it actually is sort of exponential in terms of how much time it increases in terms of how many choices you have. It means, from a design standpoint, the obvious: try at all costs to not present so many choices. And if you look, some of the designs I showed this morning from the U animal, actually, they probably didn't sit there and go, I want to do something with Hicks' law. How can I do something with Hicks' law? But they were sort of saying, I don't want to present so many choices. I'm going to try a visual way to make it somewhat simpler. This is another interesting law about human kind of memory, and that's the power law of practice. And what this says is that the task time on the nth trial follows a power law. What this means is you learn stuff through practicing. So think about touch typing. The first time you do it, you're pretty slow. Then you start to practice. The more trials you get at it, then it actually takes less time. So the graph kind of looks like this. So some obvious observations. Again, this is nothing that you will sort of suddenly rush out of here today and go, oh my gosh, like as you learn things, you get faster. That's not the point. I'm reminding you that this happens in user interfaces, and if you want someone to do something, if your design has some task, whatever you decide, this is a little complicated, but it's so crucial to my design and the way I want to use this interface, then you need to have some mechanisms that make it very, the way the class provider uses that metaphor so much that it becomes quicker for them to do. Now, a couple of things to note. The usual is that you get faster the more times you do something, but as always, it's sort of diminished return. You get a lot faster quickly, and then not so much as you go on. That might actually play to your advantage, because in a design, you might say, oh, actually, if someone can learn how to do this particular task just, a couple times, and they'll speed up, 400 or 500 times faster, then you go back to your cognitive processor and you go, oh, they're going to be able to complete this in a much quicker time period. All right. So some caveats about this. It does not really apply to things like general purpose knowledge acquisition. It's not as if you go, I learn, now I just learn faster. It's like sometimes you do pick up some strategies, but it doesn't really go at the same pace. And are we messing with this? Oh, maybe. Should I turn it down? We're trying, this is a very complicated kind of configuration that we're debugging. That's fine. I can. Yeah. Okay. All right. So the summary of that little part is when you require people to do decision making, the time to make decisions depends on the number of options, such as choosing a movie on Netflix. Learning follows a power law, and you get faster as you practice. You may think, I get it, can we just not talk about this anymore? But it is important to interface design. I mean, this is something that you will, especially the power law of practice, if it's something that requires some kind of mouse gesture or some particular hand interface gesture that's complicated, you're going to want people to practice that. Okay, I think this is the last thing I'm going to cover here before we have lunch. Fitts law. Fitts law is one of these super HCI laws that's been around for a very long time, but it's an important one, and you see it every single day in almost every interface is doing something with Fitts law. So in a nutshell, and this derives from this human model processor. So looking at it, we took this larger view to talk about sort of time to complete things and decay. This one's focused a little more on the kind of motor skill side, but it says if you are starting at some point x0 and you need to get to a target, and this get to could be moving your mouse pointer or some kind of joystick or your finger, it basically follows a very predictable law. This is the law, and roughly it tells you how much time it will take, and it's based on a couple constants which are sort of empirically derived, largely based on what the actual kind of mechanism is, meaning is it your hand, is it a mouse, is it a joystick, things like that. And these two other properties, the distance you have to travel and the size of the target, okay? So the time increases if the distance increases, but time will decrease as the size increases. So here's, you know, the most obvious example. This is sort of 1D kind of example. If you're starting from that point and you need to move to this blue target, then there's this index of difficulty, which says they're basically the same index of difficulty, which is that ratio between this distance and the size, that a small target close is the same difficulty as a big target far away. And in fact, it's very mathematically, you're able to derive exactly how difficult it will be. So some obvious things, if you move, if the target becomes sort of larger, becomes easier, okay? Or if it moves and it's sort of smaller, it becomes harder, okay? The cool thing about this is it's been proven over and over and over and over again, this law. And there's been lots of studies of how much time and the distances and motor skills around Fitts' law. So what does it mean from a design standpoint? So it actually ends up that when you are designing something, you want to do the following things. You want to bring items closer to the point of interaction. So if it's something on a screen like a cursor interface, then you want to bring them closer. Or you want to make them larger. And sometimes, and there's a little bit of a exception to that, you want to exploit the edges of your interface. So literally when someone's trying to think about, oh, how will I drag an icon to the trash? They spend a lot of time looking at the target size of that trash can. Imagine if I made it bigger or smaller, or it was closer to your mouse, how that would change your user experience. So, sounds cool. Do I ever see this? Yes, I told you. You see this all the time, every day, in all kinds of interfaces. Here's one. Bring items closer to cursor. Oh, Fitts' law, right. So when you're doing something and you select it and boom, a menu pops up. It pops up close by, not because someone thought that would be cool, but because it's well known that it will be easier to select things if the targets are close. So you don't have to have the mouse travel long distances, right? Similarly, this is similar when you're sort of selecting something and a pop-up menu occurs. So all pop-up menus are trying to exploit this. Here's another one. Lots of you maybe don't encounter them as much, but these pie menus. So if you look, usually you pop a menu and it sort of selects and you can go kind of scroll down Monday, Tuesday, Wednesday. So you move down this list. But if the task is choose Friday, then you can see the distance to Friday is a long way down. Whereas in a pie menu, once you pull the menu up, the distance to every single selection is the same. So in fact, exploiting Fitts' law again, all of these become much easier to select. Okay? How many people have encountered pie menus before? Yeah, okay. You do, they are pretty important and they give you a lot of advantage when you can use them. So, all right. How about this one? If you look, this is where if you're a really astute HCI practitioner, you'll notice something subtly different between Windows and at least when Snow Leopard came out on OS X. What do you notice that applies to Fitts law here? Yeah, the arrow icons are grouped together. Close, Fitts law, right? Easy targets, they're small still, but they're close together. Now, Windows took the strategy of, well, that might not make sense. Let's put one at each end. But think about, from Fitts law, how hard it is to hit that target, how much time on task, there's a cognitive load associated. All of that plays into this human model. So that very subtle design choice that maybe you didn't even notice is huge from an HCI perspective. Sometimes you can use it to your advantage. So if there's something you want someone to not select so easily, then use Fitts law the other way around. So maybe it says download, it says delete. Maybe you go, I don't want them to choose delete, then either make it smaller, make it further away. Okay, because those two things will then cause the user less kind of error prone, but also when they make that choice and they have to move, they are consciously have to kind of make that decision. So when you saw interfaces like this in, I think this is Office or something like that, it was moving towards larger targets. So this idea of choosing clip art or shapes, this is also larger targets. Everything was about larger targets. And it created a better user experience because when you suddenly wanted to make that selection, you've already cognitively decided. Then Fitts law took into effect, and there's just, that is the known law of the land. There's no way you kind of get past this Fitts law. You're going to take so much time to hit a target so much distance away at so much size. So if you want to make it easier, closer or bigger. Obviously, there's some ways to sort of play with that, but. All right. The other one is this exploiting the edges. So what happens when you move your mouse all the way to the edge of some screen, like on a laptop or a desktop screen? What's usually at the screen, at the edge? Well, at least in these examples, the start button was all the way down in the corner. Now, in Windows 95, they actually missed. And the final pixel, if you look, it didn't capture it. You actually had to hit that target. And if you went all the way to the end, you didn't hit it. Windows XP picked up one extra pixel row at the very bottom of the operating system, and just huge benefits from Hicks law, because now hitting it isn't stopping at the edge. You can actually exploit that edge, because when you hit it, your mouse obviously doesn't keep going, right? So exploiting the edges, these are easy targets to hit because the size basically extends out infinitely, right? There's still some size of how you have to hit that particular part, but it's important. And where do people put things on operating systems that are common that people need to access? On the edges. That's why things are at the top. That's why things are at the bottom, right? They're really exploiting Hicks law, or Fitts law, I'm sorry, in terms of getting the user experience better. But we're dealing with mobile devices. Does this still apply to us? I don't know. It ends up that the original studies actually were performed in something that's a little even more like that setting, was on a human arm and movement. So it's actually a little bit more better mapped even to what we're doing on a mobile device. So with Fitts law, the extension to target acquisition to mouth was a big result. This is Stu Card that did this work. And in fact, the tablet setting is a closer setting to what is actually backing up Fitts law. There are some kind of interesting issues here because you don't get the benefit of the edge as much, right? Where's the edge here? You kind of drift off the side. So it's harder. Sometimes it works, but not always. And it depends on how the device is held. So if you look, these are mappings of where the reachable extent of a thumb when a phone is held in the left hand here Similarly, if you hold it like this, and then if you hold it with your hand flat and interact with it like this. These are important to take into effect because now you suddenly have a mapping of where you might want to have interfaces that people could interact with. Oops. Yeah. Yeah, so let me end there because I don't want to like get into too much new stuff. I want to break so we have time for lunch. So the summary of that is just that that law applies to all kinds of interface design, and it also applies to mobile devices. There's some exceptions that I'll touch on a little bit after lunch. But take lunch, come back. We've got other cool stuff, and I'm going to critique some things that you guys sent in from Piazza. Awesome. All right, and folks that are downstairs, we missed you. Please, if you want, you can come up and mix it up, and we'll see you at 1 o'clock.